Okay, so here I am going to answer question number 3, tutorial 19C. And the question is asking about applying Dijkstra algorithm to the network from the point of view of node 5. So we talked about Dijkstra algorithm before, and it's supposed to the algorithm is supposed to find the best or the shortest route from one node to all other nodes in a network. And in order for the Dijkstra algorithm to work, it has to collect link states from all nodes, right? And then process them. Okay, so I need to do some few things first. So if you go to the slides or the textbook, you will find that we create a table. So I'm going to create a table. The table includes some columns. So the first column will be the iteration number. The second column will be the T set or the T vector, right? And I'll explain this in a minute. And then we have the information coming from the nodes. So since we are setting or we are calculating the routing table from node 5, then the columns will include the other nodes. So in each node, we'll have the length or the path or the cost to the node plus the path. So the node 2, how long to get there. Here we are seeing delays and the path. And then node 2, node 3, node 3, 4. Actually, we should start with node 1 as well. So let me just write the columns first, or draw the columns. So we need node 1, 2, 3, 4, and 6. We need 5 nodes, 5 columns. And please follow with me so you can find if I make any mistakes. These are 5 columns. All right. So initially, in the first iteration, so iteration 1, see if my tablet here collaborate with me. So in iteration 1, node 5 has only itself in the network. So we'll start with node 5 here. And then node 5 sees the path to node 1 here, or the length to node 1 and the path to it. So it sees to get to node 1, actually it cannot reach it, right? So it cannot reach it directly. So in this case, we'll just consider that this information does not exist. Node 2 also unreachable from node 5 initially, because there is no direct path. If you look at, there is no path directly to node 5, to node 2, so it cannot reach it. Okay, node 3. So node 3 we can reach from node 5 using the distance 1, right? And the path is from 5 to 1 directly. So that's 3. All right, how about 4? To 4, I can reach it also directly with a distance of 1, and the path is 5 to 4 directly. 6, 5, of course, it's the same, so we ignore it. 6, we can reach it with a distance of 2. Note the direction of the arrow, right? And the distance and the path is from 5 to 6 directly. All right. So this is the first iteration. Second iteration, node 5 looks at each one of these options and picks the one with the shortest distance, the node with the shortest distance. Here, and I get this question many, many, many times, right? So I'm gonna say this hopefully once. Here I have 2 nodes with the same distance. You can pick either one of them. It doesn't matter. It doesn't matter which one you pick, as long as you're picking the shortest distance. So here we have 1, we have 1, we have 2. So among these 3, the shortest distance would be 1. You can pick either node 3 or node 5. Absolutely no difference, right? So I'm just gonna pick node 3. So now you're picking node 3 and add it to the T matrix or vector here. All right, so now what Dijkstra algorithm does is it looks at the new network, which is now includes 5 and 3, right? And say, from this green network here, can I reach 1? No, still cannot reach 1. There is no direct path from 5 to 1. There is no direct path from, actually, there is, sorry, I didn't see it. Yes, I can reach 1 through 3, right? What is the distance? If you look at the distance here and keep an eye on the arrows, so the distance is from 5 to 3 is 1, and from 3 to 1 is 8. So the total is 9, and the path is 5, 3, 1. So now I can reach 1. How about 2? Can I reach 2? Yes, I can reach 2 through 3, and the distance, total distance is 1 and 6. So now we can reach 2 with a distance of 7, and the path is 5, 3, 2. All right. How about now 3 already in the t vector, so I'm not going to consider it anymore, right? Let's move to 4. Now 4, by comparison, can I make a path to 4 that's better than 1, distance of 1? No, of course not, because I can go to 3, but that will cost me 4, 1, and 3. So there's no change here either. So whenever there's no change, I'm just gonna write a line here, or the textbook repeats the content again, so it puts 1.5-1. So I'm just gonna put line here indicating that there is no change. All right, 6. Can I reach 6 with a better metric than 2? No, because if I go 5, 3, and 3 to 6, the distance will be 6. That's not better than 2, so there is no change here either. Okay, so now let me ask the question again. I'm just gonna differentiate between these two just to make it less confusing here. I'll just put 1, and I'll repeat this one, and I'll put dash where the node has been already included in T. So I'm just gonna repeat this one. All right, among the one that's now iteration 3, node 5 will select one of these remaining 4 nodes to be included in T. And the criteria is we're gonna select the one with the shortest distance, right? So this one is the shortest distance or the shortest delay. So I'm gonna pick 4 and include it in T. So that's 5, 3, and 4. All right, and just to make this clear, my network will be like this. So now from this green zone, can I go to 1 with a better metric than 9? Let's try. 5 to 3, 3 to 4, 4 to 1. So 1, that's 1 in this direction, and then 3, and then 7. That's not gonna work. All right, how about from 5 to 4, from 4 to 7, from 4 to 1, 8. 8 is better than 9, right? So if I go from 5 to 4, 4 to 1, the metric is 8. So let's use that. So now I can adjust my, or update my table. 8, and then this happens using from 5 to 4 directly. How about 2? From 2.
It would be better if we go from 5, 4, 2, and 1. The cost would be 6.
From where?
From 5, 4, 2, and 1. No, we have to take 5, 3, 4. So
5, 3, 4. So 5,
yeah,
3 is 1.
yeah.
3 to 4 is 3, so that's 4. And then I'll add 7, so that's 11. That's more than 9.
Okay.
Yeah. if we consider 2, so 2, I can go 1 and 6, that's 7. That doesn't give me any advantage. All right, how about 1 and then 3, that's 4, and then 2, that's 5. This is actually better than 7. So I'm gonna update my table here, and the distance now is 6, and the path is 5, 3, 4, 2.
Excuse me, sir.
Mhm.
5, 4, 2 would be better, right? It would be only 1 plus 2, 3.
5, 4, 2. Oh, yes, you're right. You're right. Right. So why didn't I see it before? Yeah. So now, yeah. So 1 and 2. So that's 3, and the path is 5 to 4 directly. Yeah. Good eye. Thank you. And no change here. No change here because we already included it. And if you see this, also, I cannot go to 6 through 4. So I'll just write it down as is here, because I still need to consider it to be included in T. Okay, so now iteration 4, among these 3 remaining nodes, the 6 has the shortest distance. So I'm gonna include it in my topology here, in my T vector here. And as I did before, so I'm gonna look at this change and see if it affects the path to 2 or 1. So my network now, let's delete all of this. My network now includes 5, 6, 4, and 3. So by including 6, do I get any advantage reaching 1 or 2? No, because it's actually in the other direction. All right, so no change. So let's go to iteration 5. Iteration 5 will select either 2 or 1. So it's gonna select 2, of course, because it has the shortest distance here. So I'm gonna go 5, 3, 4, 6, and 2. Okay, and my network now includes all of this. So can I reach 1 with a better metric than 8 by adding 2? Right? So to get to 2, my best path was from 5 to 4, right? To get to 2. 5 to 4. And then go to 2. So that's 5, 4, 2. That's 3. And then if I see here, I see I can go to 1 with the metric of 3. So 1, 2, and 3. That's 6. That's better than 8. So I'm going to put 6 here. And then now it's 5, 4, 2, and 1. by the way, here I should as well. And this is 2. Forgot to write 2 here. Okay. So now the last iteration, obviously there's nothing else left except 1. So I'm going to include it in my T. And now all of them are done. So if you look at the result here, you see that the remaining items in the last iteration are the shortest path to every node. So if I want to go to 1, I go through 5, from 5 to 4, 4 to 2, 2 to 1 with a metric of 6. If I want to go to 2, I can go from 5 to 4, 4 to 2 with a metric of 3. To 3 directly, to 4 directly, to 6 directly, right? If I want to verify that, I can go and say, okay, so let's draw the picture again. From 5 to 6, I can go straight here. From 5 to 4, I can go directly here. From 5 to 3, also directly. Right? From 2, I have to go 5, 4, and 2. And to 1, I have to go 5, 4, 2, and 1. So you'll find that you built a tree actually, and these are the shortest distance, or in this case, it's the lowest delay. Okay. So that's one example where you are looking at the Dijkstra algorithm from node 5, right?